Here's a subtraction of the Raman response by Z1 at close to room temperature 280. So when we decrease temperature, we see a dip and a time. We see a dip and a time. And we're above TC. And this dip and the time, which corresponds to a transfer of spectral weight, is not due to superconductivity because it appears above TC. And now to show you the effect of superconductivity, please look at the left panel. When we enter into a superconducting state, we have a hand here which grows up at low energy, which grows up here, as you can see here, the blue line, and it grows up again, and that is the nodal superconductor. So at the end, at low temperature, we see both the nodal superconducting gap and the end of the charge density. So we are confident that it's the charge density wave for many reasons. So the first one is that if we compare our results, deep and amp in Mercury 1, 2, 3, it's very similar to what we get from the well-known erbium 3 telluride, which takes charge density wave order, and this deep and the amp, this is the blue curve here, deep and the amp disappears above the transition temperature of the charge density wave, which is about 287 K. This is the red curve. So we have exactly the same structure. The second reason is looking at the transition temperature of the charge density wave. So we can define the transition temperature of the charge density wave by measuring the integrated area of the amp and look at its collapse. When this integrated area collapse, we can define the transition temperature of the charge density wave. So we do that for several dopes. For strongly undoped system with a critical temperature of 105 Kelvin, this is the Mercury 123, and for an underdoped sample, a slightly underdoped sample, and finally for an optimal dope sample. And we measure at each time the integrated area of the peak as a function of temperature to find where it collapses to define the transition temperature of the charge density wave. So we can see that it's non-monotonic, and this is reported. It is non-monotonic, and it's exactly what we get in YVCO or in Mercury 12001 from X-ray diffraction on NMR measurement, where they find that the transition temperature of the charge density wave as function of the peak is non-monotonic. But here is a sample which has not yet measured by NMR X-ray diffraction. So the idea is to take exactly the same sample as the sample which has been already measured by X-ray diffraction. So we get the Mercury 1201 and we detect the amp. We take the YVCO and we take the amp also. And then, as a function of temperature, we can determine the integrated area of the amp and define the collapse of the integrated area to define the transition temperature of the charge density wave. So we find 200 K for this compound, for this specific doping, and here we find 140. So now, if we report our Raman data with the red spot on the phase diagram get from the X-ray diffraction and NMR diffraction, we see that it fits pretty well with the transition temperature found by the other spectroscopy technique. Here we have performed a measurement on YVCO of two different doping levels. This is two spots here, and it also fits pretty well with the transition temperature of the charge density wave got from both NMR and X-ray diffraction, which make us confident about the nature of the M that we find in Raman spectroscopy to be the charge density wave signal. So now we can go further And by looking at the maximum of the energy of this peak, we can determine the energy of the charge density wave. So we define energy scale of the charge density wave as the top.
Alain, you have 3 minutes. Is it okay?
Yes, okay. Yes, okay. So, this is the energy of the charge density wave here. And of course, we can see it more clearly if we make the subtraction between the Raman spectra, the lowest temperature, and the Raman spectra just at the at the transition temperature of the charge density wave. So here we get this maximum. We see that it decreases in energy, but we are a little bit bothered here by the signal of the superconducting gap, as you can see. So the idea is to make the measurement just below TC, but still in the superconducting state to benefit of the long quasi-particle life. So if we do that, you can see I reduce considerably here. I reduce considerably the signal of the superconducting gap, and I can emphasize the signal of the energy of the charge density wave. So now we can plot, this is a good triangle, we can plot the energy of the charge density wave, and it's very close to the energy of the antinodal superconducting gap. And these three energies linearly as function of the group and follow T star, and not follow TC. The only one we follow TC is the nodal superconducting gap. So let me summarize. The energy of the charge density wave is proportional to the energy of the antinodal superconducting gap, and it's proportional to the pseudo gap and follow T star, while the energy of the charge density wave is no more proportional to the transition temperature of the charge density wave, and no more proportional to TC. Sorry?
Summarize, yeah.
Just to summarize, the energy of the charge density wave is linearly as function of the group is non-monotony, exactly as the antinodal superconducting gap is decreased linearly, does not follow. So these two orders are non-conventional, which then cannot be decreased by a limit in theory because they are not proportional to the transition temperature. And the last point is that the energy of the charge density wave is very close to the energy of the antinodal superconducting gap. They are proportional to the pseudo gap and follow T star. So the scale of the antinodal superconducting gap, charge density wave gap are intimately connected and related to the pseudo gap. This allows us to make the following conjecture is that the pseudo gap phase will be a kind of primary order which controls both the antinodal superconducting order and the charge order. And this paves the way for new theoretical approaches for understanding the pseudo gap phase, such as the fractional fraction proposed by Pepin, and there is also other proposals by Patrick Lee and Ampere and Berry, etc. And all these theories have a common point. They propose that there is a net momentum for a curve which allows to combine superconducting order and the charge density. And this is in agreement with our expected. Thank you for your attention. I'm sorry for the delay.
Let me ask a question to Alain, just for the discussion. So Alain, this is a fantastic set of data, and what it tells is basically like charge density wave is not an epiphenomenon, but it's kind of phenomenon of magnitude comparable to spare conductivity. Would you agree with this? And how would you explain then that other probes had so much problem? I mean, put so much time to observe it. Like X-rays, or it took very long. Even for you, actually, with Raman, it took long to. Is it hidden in a sense or something like that?
Oh, there is the point is that, as mentioned previously, when we have to find the good way to detect the charge density wave and especially the energy of the charge density wave, because the effect of the pseudo-gap is huge and destroy all the quasi-particles along the principal axis of the movement. So if you want to detect the charge density wave, you have to go a little bit away from the antinodal region. This is the reason why we are looking in the nodal region to detect it. And the other point is that Raman spectroscopy is an energy probe. It's not a momentum result probe. So if you want to try to detect the charge density wave with a momentum result probe, is not easy for the charge density wave because the charge density wave has a very short range or length. So we need to use an energy probe to detect it. And this is the case of Raman spectroscopy. This is one of the reasons why it's difficult from angular emission spectroscopy, which is a momentum probe, a momentum result probe to detect easily this charge density.
Okay.